So to try and understand what a p-value is, we're going to flip a coin 25 times and take a look at the results. Now, that would take a while if we're doing this by hand. So if you click over here, generate one sample, there we go. So I flip a coin 25 times and I got 12 heads. Are you going to doubt my null hypothesis that the probability of a head is actually 50%? I don't think so. In fact, what we would expect under the null hypothesis is to get 12 and a half flips out of 25. Of course, you can't get 12 and a half. So now if you got 12 or 13, that's about as least of a surprising result as you can expect. Let's generate a couple more. Let's generate another one. And I got another one with 12. Now you probably got something different, and that's fine. There we go, 15, 11. But this is getting boring. I wanted this to be a little more fun and interactive, so let's generate 100 or maybe even 1,000. So there we go. Now we're starting to get some pretty interesting data here. So I've got 1,104 samples personally. You might have a slightly different number. That's okay. All of these come from flipping a fair coin 25 times. At what point would you say, you know what? Boy, I just don't think that you can get 18 heads out of 25 by flipping a fair coin. Or maybe you set the boundary at 19 or 20 or whatever you want. Did anyone get anything higher than 20? Did anyone get 21 or 22?
No.
No? Okay. I mean, that'd be quite a string of luck. In any case, at some point, you're going to set down a marker and say, you know what? Beyond this point, I don't think this is true. So click right tail. And when I click right tail, it puts a little marker down for me on 17 with a probability of 2.5%, meaning there's a 2.5% chance that I'm going to get an observation out here. Meaning if you decided, you know what, 17 is my cutoff. If you got a 17 out of 25 heads, at that point, I just don't think that it's true that you had a fair coin. I think it's false. You're rejecting it. This probability then of being here in the tail, that's your p-value. That's the probability that the null hypothesis is true for your given data. So out here in the tail, there's only a 2.5% chance that you're going to get a value this extreme or more extreme. So it's unlikely. You can change this value if you'd like. If I click here and make that cutoff 18, now there's only a 1.5% chance that I'll get a value out here in the tail. So if my cutoff was 18, I said, you know what? At 18, I'm going to reject the null hypothesis. There's a 1.5% chance that I could get data that would lead me astray. It would lead me to believe that H naught is actually false when H naught really is true. You can click two tail. Now it's going to put data up on two tails. So it's spreading that probability out amongst two tails. You got 2.5% here, 2.5% here. There's a 5% chance of being out there in the tail. So there's a 5% chance that you could be wrong for data that looks like this in here in the red. Anywhere in the red, data could be leading you astray. It's a chance that you take when you're making a decision in a null hypothesis. We like this value to be as small as possible. Smaller values of P make us more and more confident that we're not making a mistake. Can you make a mistake? Sure. If my value was 20 up here, then there's less than a 1/3 of 1% chance that I get something like this in my data. This is the probability that I got something like a 20 or a 21 and reject the null hypothesis, even though it's true. Okay, let's try one more here. And let me give you another link. Same website, just kind of zooming you forward to a different spot in that website. If you want to open this up in a different link, that's fine as well. This is a study done on mice. And what the researchers did was they put mice in two different conditions. One of them was to sleep at night with a light on, and one of them slept without a light, slept in the dark. And for reasons that I can't explain, they assigned the mice this way. 10 mice had the light on, 8 mice had the light off, slept in the darkness. And here's their body mass weight gain. Those who slept in the light, those who slept in the dark. Now, if you had this data and you're trying to determine, does sleeping in the light or sleeping in the dark make a difference? How could you approach that? What would you do to try and figure out, well, do people who sleep in the night gain more weight? I guess I said people. Do mice who sleep in the night, sleep in the light, gain more weight than those who sleep in the dark?
Yeah.
Looks that way. Well, why does it look that way, though? What?
There's
What
more
would
data for light than dark.
There's more data? That's true. So there's more data. What else could you look at to try and determine, are these groups the same or are they different?
The highest point of data in light is 11.
Mm-hmm. So this one really put on a lot of weight. In fact, you got several that put on a lot of weight. And over here, not so much, but you do have one that was lighter. This one only put on 1.71 grams. The lightest one over here was 2.27. So how can I compare these in a way that helps me decide, does the light have an effect or not? All right. Yeah, I think somebody put in the chat talking about the averages, right? So you can look at the average here, and let's do that. I don't know if my data came through or not on the link that I sent through, but if it did, just click reset plot here. And here's the data. So here's the data from the dark sample. Here's the data from the light sample. The mean from the first set is around 4.2. Mean from the second set is about 6.72. So the difference in those means is one way that you can look at whether or not there was actually a difference amongst these mice in their weight gain. And that's a reasonable way to look at it. Is there a difference? Now, when we subtract the mean weight gain from one versus the other, light minus dark, we get 2.62 grams. Is that significant? Is that a meaningful difference to the point that you're like, oh, yeah, definitely being in the light causes more stress, causes you to gain more weight? Or is it kind of like, eh? Well, here's how we're going to find out. We're going to generate random samples from this data. I'm going to treat this whole data set. I'm going to put in the light and the dark together and just sample from it and randomly assign them to light and dark down below. So if I generate one sample, here we go. This is called bootstrapping. You're sampling with replacement out of this population. You're treating them as all one group and then randomly assigning them here. And if you look at the differences that you get, the difference from this sample to this sample, now I got a difference of -1. If I click another sample, this time I get a difference of -0.37. So just how unusual is it to get a difference all the way up here of 2.62? Is that really unusual? to the point that I can start saying, you know, I don't think that these come from the population with the same mean. We're going to do what we did with the last one. That is generate, say, 1,000 samples and generate 1,000 more if you'd like. Now, this is the distribution of differences if, you know, the weight gain really didn't make a difference, it was just assigned at random. Is it unusual to get something way out here like our original data was, which is a difference of 2.62? Is it unusual to get something way out there? Or could that happen easily by chance? Could it easily happen by chance that I get these results? Tell you what, click right tail. That should put on some area in the right tail. There's only a 2.5% chance that just by luck that I'll get something greater than about 2.485, meaning that it's really unlikely that I would get these results just by chance. So one of two things happen. Either I got this result just by chance, or there's really a difference between these two means. I should reject this possibility that mu1 equals mu2. And the chance that I get something like this, 2.262, let's just change that to 2.262, about 3.7%. So could it happen? Yes. Is it likely to happen? No. But for us in this data set, 2.262 has a p-value of about 0.037. So it's unlikely that you're going to get something like this by chance. Could it happen? Yes. So now the higher this value is, 2.65 maybe, the smaller the chance of the null hypothesis being true for your given data. So the smaller the p-value is, the more confident you are in rejecting H0, because it means it's less and less likely that H0 could be true for your data. You could be making a mistake, but it's less and less likely. Okay, comments or thoughts on p-values here. So I spent a little extra time here. I want you to understand them. The p-value is the probability that H0 is true for your given data. And if that p-value is really, really small, you have one of two decisions. Either you got unlucky, or lucky, depending on how you want to think about it, but you got unlucky with this value, and H0 is true, or that H0 is false. So as statisticians, when the p-value is small, less than some value of alpha, we always make the decision that we think H0 is false. Comments or follow-up on that?